Hi, in this video I'm gonna give a brief lecture on shear stress and viscosity. Viscosity is a property of fluid that describes the fluidity of a fluid. We have absolute viscosity or dynamic viscosity or simply just the viscosity of the fluid, which is designated by the Greek symbol mu. Also, we have kinematic viscosity, which is designated by the Greek symbol nu. And the relation between these two viscosities is that mu is rho times nu, where rho is the density of the fluid. Mu has a dimension of Newton times second over square meter. Density has a dimension of kilogram over cubic meter. And nu, or kinematic viscosity, has a dimension of square meter over second. But what is shear stress? Shear stress is designated by tau, which is a multiplication of mu and the velocity gradient, where here mu is the absolute viscosity or dynamic viscosity or simply just viscosity, and du over dy is the velocity gradient. For example, here the flow of a fluid between two parallel plates. Here this plate is a fixed plate where the velocity at the wall here is 0. And this plate on top, the force is acting on it, so it's moving with velocity u. So here the velocity is u. And the profile of velocity, as you can see in this example, is linear. We're going to solve 3 problems. And the first problem says that the velocity distribution of the flow of a Newtonian fluid between two fixed plates, these two fixed plates, is given by this equation, where v here is the mean velocity, and the fluid in between these two parallel plates has a viscosity of 0.04. Also the value of the mean velocity and also h, which is the half of thickness of the fluid film, is given. So it says that determine the value of viscosity here at the middle of this channel, and also at the bottom, at this surface. So as you know, shear stress is mu times the velocity gradient. Here we have the velocity profile. So the velocity gradient would be equal to minus 3v divided by h squared times y. So in part A, we want to solve it for y equals minus h at this surface. So du over dy will be equal to 3v divided by h. So tau would be mu times 3v over h. and here we have the value for mu, for velocity is given, and also h is given. So we can find the shear stress at the bottom plate at here. But what would be the value of shear stress here at the center of this channel? So at y equals 0, du over dy, when y is 0, du over dy would be equal to 0. So the shear stress would be 0. Always when we have a flow between two fixed plates, the shear stress at the center line would be 0. Because as you can see here, the velocity gradient is 0. As you can see, the slope of the velocity profile at this point is 0. The next problem says that two flat plates are oriented parallel above a fixed lower plate. Here is the fixed lower plate, and here are the two flat plates. The top plate, located at a distance b above the fixed plate, is pulled along with speed v, and the other thin plate is located at a distance cb, where c is between 0 and 1 above the fixed plate. This plate moves with the speed v1, which is determined by the viscous shear forces imposed on it by the fluids on its top and bottom. The fluid on the top is twice as viscous as that on the bottom. Plot the ratio of v1 over v as a function of c for c values between 0 and 1. So to solve this problem, for the thin plate that is pulled with velocity v, there are two forces. One is due to the shear stress on the bottom of the plate, which we show it as FL, and one on top of it due to the shear stress acting on it because of the presence of the fluid on the upper surface. And these two forces must be equal to each other. So Fu is equal to Fl, where here the forces are due to the shear stresses, so it would be shear stress on the upper surface times the area that the shear stress is acting on must be equal to the shear stress on the lower surface times the area. These two areas are the same, so these two cancel each other out. So the shear stress on the upper surface would be the viscosity of upper surface times the velocity gradient at upper surface must be equal to that of the lower surface. But what's the viscosity on the upper surface is 2 mu, and here the velocity is v, and here is v1. So v minus v1 divided by the y location, here is b and here is cb. So it will be b minus cb is equal to the viscosity of the lower part, which is mu, times the velocity gradient, which here the velocity is v1 at cb and here is 0 at 0. So it would be v1 minus 0 divided by cb minus 0. So from this equation, mu will cancel each other out. So 2 times v minus v1 divided by b times 1 minus c is equal to v1 divided by cb. And from here, b and b will cancel each other out. And if we divided both sides by v, we will end up having v1 divided by v is equal to c. The last problem says that a 10 kilogram of block, this one, slides down smooth inclined surface as shown in this figure. Determine the terminal velocity of the block if the 0.1 millimeter gap between the block and the surface contains some kind of oil at 60 degrees Fahrenheit. Assume the velocity distribution in the gap here is linear, and the area of the block in contact with the oil is 0.1 square meter. And the velocity for this fluid is also given. So here in this problem, there is a weight of the block acting downward, which this one has a component in this direction, which is W sine of 20 degrees, and also one in this direction, which is W cosine of 20 degrees. And also the shear stress here is acting in this direction. Here is the force due to shear stress. So if we write the summation of forces in each direction must be equal to 0, so W sine of 20 degrees must be equal to the force due to shear stress. So W sine of 20 degrees must be equal to tau times the area, where here we have the mass of the block. So its weight would be its mass times gravity times sine of 20 degrees must be equal to tau is mu times the velocity gradient times the contact area. Mu is given, or it must be given. We can find it from the tables. And the velocity gradient, since the velocity is linear here, this one would be equal to v divided by h, where v is velocity at the upper surface minus velocity here, which is 0, divided by this distance, which is h. So from here, the velocity would be equal to mg sine of 20 degrees divided by mu times the area, which would be equal to 0.0883 meter per second.